Hey, AB Chemistry. Welcome back to Chapter 8. We're going to talk about just a couple more details and then we will be done with this chapter. So, the first one is a promise topic that we were talking about when talking about the localized electron model. So, we talked about how sometimes you can use the Lewis dot structure rules and come up with a couple different compounds that can satisfy the octet rules in different ways. And what we need to be able to do is have a method that helps us to predict the molecule that actually exists. And our way of doing that is called formal charge. So, welcome to formal charge. Okay, so it's just a method that helps us decide which Lewis structure matches the actual molecule. It's kind of like an addendum to the Lewis structure, the localized electron model. Okay, so here's how formal charge works. Basically, you take all the unshared electrons that are assigned to an atom, and then you also take half of the bonded electrons that are assigned to an atom, and you subtract that from the actual valence electrons on that atom. So if we take this Lewis structure for the cyanide ion, we can do a formal charge for carbon and we can calculate a formal charge for nitrogen. And then basically, if we do that for all the atoms for each of the molecules, whichever molecule comes out with less formal charge is the better model. That's the one that's going to actually predict the how the compound exists. So let's just practice calculating formal charge on the cyanide ion really fast, and then I'll show you how this works with boron trifluoride that we looked at before. Okay, so if we're going to calculate formal charge for carbon, for example, we're going to take the valence electrons from carbon, which is 4, and then we're going to subtract off all the unshared electrons plus half of the bonded electrons. So around carbon, we have 1, 2 unshared electrons, and then we have 1, 2, 3 bonded electrons. Notice I'm taking half of the bonded electrons and giving them to carbon. So that would be 5 total electrons. So carbon has a formal charge of -1. And then nitrogen will do the same thing. We'll take the valence electrons that nitrogen has, which is 5. We'll take all of the unshared electrons, which is 2, half of the bonding electrons, which is 3. So 5 minus 5 equals 0. So carbon has a formal charge of 1. Nitrogen has a formal charge of 0. The sum of the formal charges, notice that in this case, the sum of the formal charges is equal to the charge of the ion. And so this can be used to predict what model actually exists. So let's look at an example of that. Let's look at boron trifluoride again. So we drew this one already, and it can be drawn in 2 different ways. It can be drawn where boron has less than an octet. It can also be drawn where boron has a full octet. Okay, so what we're going to do is calculate formal charges for every atom on both of these molecules, and then we'll compare how the formal charges come out. Okay, so now would be a good time to pause the video, or at least don't look at the video and look at your own paper and calculate these formal charges. See if you get the same formal charges that I get. All right, so you can see the formal charges that I got. On the molecule that's on the left side, every single formal charge is a 0. On the molecule on the right side, I have 2 zeros, I have a -1 and I have a +1. So because this molecule on the left here has all formal charges of 0, it has less formal charges, and so that is going to be the better molecule. This one on the other side, it does satisfy the octet for every single atom, but it does that at the expense of occurring formal charges on a couple of the atoms. And so this one is not the better molecule. And what the formal charge allows us to do, it allows us to evaluate a couple different Lewis dot structures and predict which one is going to be the one that actually occurs. And this matches our model. This model matches reality. Boron trifluoride actually exists in this arrangement that we see on the left here. It does not exist on the arrangement we see on the right here. So formal charge helps us to predict the Lewis structure that matches reality. Does that kind of make sense? Okay, so you should be able to calculate formal charges for atoms within a molecule, and you should be able to use the formal charges to predict the molecule that's going to match reality the most. And that's going to be the one with the least amount of formal charges present. Okay, so we have another example here. We can do that one together in class. And then this brings us to resonance structures. So resonance structures is another little addendum to the localized electron models. And what happens with resonance structures, again, is that what the model shows us doesn't match what we observe in real life. And so when that occurs, when we find this point of breaking for our model and it doesn't actually predict what we see in real life, what we have to do is change the model. And so our model's about to get changed slightly. Let me tell you the problem here. Okay, so we're going to look at ozone in this example. So we're looking at the molecule of ozone. If you go ahead and you write out the Lewis structure of ozone, so you add up all the valence electrons, connect them all to a central atom, which is going to be oxygen, distribute them all until they all have an octet. In this case, we have to try multiple bonds. What you're going to get is a Lewis structure that looks like this. So notice I have an oxygen on the far left that has an octet. I have an oxygen in the middle that has an octet in a different way, right? On the left, you have 3 lone pairs. In the middle, you have a single bond, a double bond, and 1 lone pair. And then on the third side, you have 2 lone pairs and a double bond. So all 3 oxygens in this molecule are actually different oxygens, right? We can label them like A, B, and C, oxygen A, oxygen B, oxygen C, and they're going to show up according to our Lewis molecule, our Lewis structure that we've drawn. They're going to show up differently in the model. So think about this real fast. This might be a good place to pause the video and think, maybe jot a couple things down. How will oxygen A, B, and C be different in the molecule? If we were to build a model of this, how would those 3 oxygens be different from one another? Pause the video here and think about that. And the way that they would be different is in distance from each other. So remember we talked about how single bonds tend to be long and double bonds are short, right? So if this is how ozone actually existed, the model would actually look something like this. That's what the molecule of ozone would look like. But that's not what we observe. Ozone doesn't actually look like that. Ozone is not lopsided. Ozone is very symmetrical. But what's interesting about ozone is the bond in ozone is not as long as a single bond. it's also not as short as a double bond. Oh, I didn't draw a very symmetrical molecule, did I? Let me try that again. All right, that's a little bit more symmetrical. Okay, so what we see is ozone, the actual molecule of ozone floating around in our atmosphere, protecting us from radiation, right? It does not match the Lewis structure that is predicted for it because A, it's symmetrical and the Lewis structure is not symmetrical. B, the bond lengths are not a single bond as predicted or a double bond as predicted. They're this like halfway length. The length, if the double bond is a length of 1 and the single bond is a length of 2, the bond that actually occurs in ozone is a 1.5. So it's the Lewis structure is not matching reality for those two reasons. A, the molecule is symmetrical. B, the bond length is like a 1.5 bond length, which is not predicted by the Lewis structure. And so what we assume in this case is that you can draw the Lewis structure in two different ways. You can draw the Lewis structure with a single bond on the left side, double bond on the right, or you can draw the Lewis structure the opposite way. Single bond on the right, double bond on the left. Now, this may look very similar to you, right? How is this different? It's kind of like your hand, okay? Let's say, here we go. Let's say I hold 2 pens, right, in my hand, okay? Well, I can flip the pens the other way, but then you see the front of my hand. You see the palm of my hand. It's different. You see the back of my hand. It's different. So I can't just rotate the colors and have the same molecule present because the molecule actually reverses like this. And the same thing is happening in a molecule also. The molecule also has very definite structure, and it has very definite bond lengths. And so you can't just flip a molecule. We kind of saw that a little bit in organic chemistry when we were trying to write all the different isomers. But as you get farther and farther and farther up in organic chemistry, you'll start dealing with this phenomenon of like flipping molecules. They call it chirality. It's a chiral molecule. It starts with a CH. CHIRAL, I believe. So if you want to look into this a little bit further and really understand chirality, I'm pretty sure I didn't just make up that word, or understand chiral molecules, you can look it up. It starts with a CH. But this is the idea, like we can have the double bond on the right, we can have the double bond on the length. It should lead us to multiple ozones, but what we observe in reality is neither one actually occurs. And so the way that we change the model is we say that when this occurs, when you can have a bond moved within a molecule and not have that bond connect different atoms, notice it's always an oxygen to oxygen, we say that the molecule has resonance. And it's a resonant structure. The molecule has resonance. And here's what that means. It means that these two elements, or these two electrons, are not actually localized. Remember, we talked about this molecule as if we have localized electrons in the bonding region, right? Those electrons are stuck in between those two atoms and they cannot move. We call that a localized electron. And then we also have delocalized electrons, which are on the atom itself, but they can kind of move and adjust, right? They're not stuck on one aspect of the molecule. They are delocalized, okay? So that's what this model is built off of. The model is built off of two different types of electrons, localized, which we find in the bonding region, and delocalized, which we do not find in the bonding region. But here's the deal. These two electrons that should be localized actually are not. These two electrons can actually move in between these two bonding regions. And so they spend half of their time on the left side of the molecule and half of the time on the right side of the molecule. They can kind of shift back and forth. And because they spend part of their time in one place and part of their time in the other place, then the bond actually becomes more like a 1.5 bond. It's not a single bond because it has extra electrons that spend time there sometimes. It's also not a double bond because those extra electrons don't spend their time there all the time. So they kind of swing back and forth between these two structures, and they create this 1.5 length bond, which is what we tend to see in the model. We actually do see this bond length that's somewhere between a single bond and a double bond. Okay, so that is resonance. It occurs whenever you can draw a single or double bond in two different places, but it's still between the same atoms. Let me show you an example of something that would not have resonance. If you had like S, C, N, and you were trying to decide, do I put the double bond between the carbon and the nitrogen, or do I put the double bond between the sulfur and the carbon? This would not be a circumstance where you have resonance because the double bond is moving, yes, just like in resonance, but it's moving between different atoms. Sulfur carbon, nitrogen carbon. Those are different atoms. And so in this case, we would say we need to do formal charges here to figure out which one is the best section, and we need to choose that molecule, right? That would be a case of using formal charges to choose one of these. However, if you have, let's say, carbon-carbon bond, I don't know what it would look like. You'd have some other things attached to it, right? But let's say you come and say, all right, I could have a double bond here, or I could have the double bond here. Notice that the double bond that we have to make a decision for, it's either between carbon and carbon, or it's between the other carbon and carbon, right? These two would have resonance. We would not use formal charges to decide which one is better because they would come out to be the same formal charges, right? And what we would assume happens is that this carbon-carbon bond, both carbon-carbon bonds are actually about like a 1.5 bond length. It's not as long as a single bond. It's not as short as a double bond. It's like a 1.5 bond length. We would say this has resonance. Okay, a couple technical details here. When you say that something has resonance in our class, in inorganic chemistry, what you do is you have to draw all possible drawings and then draw arrows between them, a double-headed arrow between them. So what is the Lewis structure for ozone? It's this. You have to draw this whole thing with an arrow in between them that indicates resonance. If you draw one of these, it's an incorrect answer. You have to draw both. And if there's 3 different solutions, you have to draw all 3. If there's 4 different solutions, you have to draw all 4. Now, the test is probably not going to make you do that. The test will probably make you draw 2, maybe 3 if they're feeling especially grumpy that test writing day. Okay, but usually it's something that's very doable, but you do have to recognize that it has resonance. You could move that double bond and still get a consistent molecule that would come out with all the same formal charges, right? And then that would be a resonant structure. I want to show you a couple more examples of this. A really famous example, ozone's really famous. Again, this is one of those scenarios where there's only so many examples to draw on. So if you really work through this and practice it, you're probably going to see all the possibilities that they could throw at you on the test. Ozone is one of them. Another one is called benzene. So benzene's a really famous molecule for multiple reasons. First of all, it's nonpolar. So if you need a nonpolar solvent, benzene is one of your options. Now, benzene also comes with its own host of complications. I believe it's carcinogenic. We don't have any in our storeroom because there's reasons for us not to store it. But if you go to college, you'll probably deal with benzene. It's one of the most common nonpolar solvents. It's a 6-carbon ring. Ring molecules are also super unusual. Usually, if you have a molecule that forms a ring, it's going to be a ring of 5 or a ring of 6. And so this is your all-carbon ring of 6 called benzene. So notice that if we draw the Lewis structure of benzene, there's 6 carbons, 1, 2, 3, 4, 5, 6. You can draw the double bond, and you can draw it with alternating double bond and single bond. So it always comes out with 3 double bonds and 3 single bonds. But notice you can draw it this way, or you can flip it and draw it the other way, right? So there's really 2 different ways you could draw this molecule, which means it's a resonant molecule. It has resonance. In organic chemistry, you're not going to see it drawn out like we would draw out our Lewis diagram. If they ask you to draw benzene on the test, you should draw it exactly like this. Draw both possibilities with an arrow in between them and box the whole shebang, right? In organic chemistry, they really get sick of drawing bonds, carbons, and hydrogens, and so it ends up looking like this. Oh, actually, that's not true. Notice they still have both of them drawn out here. The double bond just becomes 2 lines. The single bond becomes 1 line. Each point in the line is a carbon, and then hydrogens just get dropped off. They figure you can figure out hydrogens if you really care about them. Or they draw the molecule a third way to draw it in organic chemistry, not in our chemistry, is this right here. They'll notice carbons are still the points. Hydrogens still get dropped off, but they draw it with a completed circle in the middle, and that indicates resonance. Sometimes what you'll see also is a dashed line around the middle instead of a solid line. So in organic chemistry, your options open up to you, but in inorganic chemistry, you must draw it like the blue box. And then the benzene bond lengths, when they go and figure out the benzene bond lengths, they do indeed find that the bond lengths are, actually not the one that I just circled. They're like a 1.5. If you have a carbon-carbon single bond, that single bond is going to be 1.54 angstroms long. A double bond is 1.34 angstroms long. And the bond in benzene actually comes out to be 1.4, which notice is kind of in the middle of the other 2, indicating it's not a single bond, it's not a double bond, it's like a 1.5 bond. Okay, so there's another example of resonance. That's a really common one that comes up. You'll see a couple more in the problems of your book. We'll talk about one together. We'll do this one live. And then here's a practice multiple choice. We'll do this one live also. Okay, so the last thing we really have to talk about is bond enthalpy. So thermodynamics meets bonding. We talked about lattice energy. Lattice energy is the energy required to break the bonds in a lattice. Bond enthalpy is very similar, only instead of dealing with a lattice, we're dealing with a discrete molecule. Remember, discrete means it's individual and set apart. So if you have like carbon monoxide, for example, CO, if you have that listed, it's literally one carbon bonded to one oxygen. In contrast to an ionic compound like NaCl, is actually lots and lots and lots of positives bonded to lots and lots and lots of negatives, right? So an ionic, we call it an ionic compound because it's not actually, it's a ratio. We call this a covalent molecule because it indicates that it's a discrete or individual molecule that's not attached to a whole bunch of things. The atom count is actually 1-to-1, whereas the atom count in sodium chloride is not actually 1-to-1. So lattice energy and bond enthalpy are basically the same thing. They're just describing, the energy to break one bond inside a lattice versus the energy to break one discrete bond. Okay, so bond enthalpy is our last topic to talk about. It's the enthalpy required to break apart a bond for 1 mole of a gaseous substance. So, for example, we have atomic chlorine here, the chlorine-chlorine molecule. So we're breaking this bond in the middle of the two, and we're breaking it into 2 individual chlorine atoms. The enthalpy required for this is 242 kilojoules. Notice that it's positive because anytime you break a bond, you need to input energy into the system in order to break it. You can think of like breaking glass. Anytime you break glass, you have to input energy into the system in order to break it. If the molecule you're looking at has more than one bond, like methane is a good example of that. Inside the methane molecule, there's actually 4 carbon-hydrogen bonds. So in this case, the bond enthalpy that you get out is an average. So if you have enthalpy and you remove the first hydrogen, technically that's going to take a different amount of energy than removing the second hydrogen. And that's going to take a different amount of energy than removing the third hydrogen, and so on and so forth. And so rather than talking about like bond enthalpy 1, bond enthalpy 2, bond enthalpy 3, bond enthalpy 4 for a molecule like methane, what they do is they take all 4 bond enthalpies and they average them. And then that's what gets listed as the carbon-hydrogen bond enthalpy. So just a technical definition there to kind of understand. It doesn't really practically impact your life a whole lot as you're doing these calculations, but something to keep in mind. Better to understand the whole picture than just part of the picture, right? So actually, I think I circled the wrong thing on here. I think it's this is the total amount of energy to break off all of the carbon-hydrogen bonds, and so that amount of energy gets divided by 4, and 415 kilojoules per mole would be the energy for just one of those bonds. 1 mole of those bonds. All right. Couple details. Their bond enthalpies are super consistent. If you break a carbon-hydrogen bond off of methane, it's really similar to breaking a carbon-hydrogen bond off of like carboxylic acid. And so they get tabulated and put into appendices. So if you look in the back of your book, you will find an appendix with all these bond enthalpies listed because they're so consistent. Remember that appendix is not going to be exact when you calculate a bond enthalpy. It's not going to be exactly that, but it's going to be really, really close enough to be useful. And so that's why we use this. Always, bond enthalpies are always positive. Energy is always required to break a bond. You usually get energy out when you're forming a bond, not always, but usually. If the bond enthalpy is greater, you can assume that the bond is stronger. So bond enthalpy becomes this indicator of bond strength. If there is a stronger bond present, then the molecule is less likely to enter into a chemical reaction. So we see this like logic flow here, right? Greater bond enthalpy means stronger bond, means less reactive molecule. So those three things can be tied together. For example, the silicon-oxygen bond is one of the strongest silicon bonds that forms. And therefore, silicon-oxygen bonds are one of the most common compounds on Earth. In fact, 90% of Earth's crust are silicates. 90%! Did you know that? Do you know what one of those looks like? You should go Google it. It's also known as quartz. If you crack open a geode, this is what you find inside. Quartz can be really pretty, by the way. I think agate might also be another name for quartz. Some little people that I'm around and quite fond of happen to be super into geodes right now, which is why I know all these random facts about geodes. Okay. Anyway. Okay, so bond enthalpies are used for a bunch of different reasons. You're going to like the formula. It's going to look super familiar to you. It's used to estimate enthalpies of reactions. It's used to estimate if the reaction is going to be endothermic or exothermic. It can be used if enthalpy of formation is unavailable. So here's a good distinction to make. An enthalpy of formation is different than a bond enthalpy. This would be a really good place to sit down and do like a Venn diagram and figure out, okay, bond enthalpies versus enthalpy of formation. How are they similar? How are they different? Just to kind of separate those two in your mind. They can be very similar, but they represent very different concepts. Okay, so in order to calculate a bond enthalpy, there's basically two steps to it. First of all, you have to figure out all the bonds you're going to break and tally up the energy it's going to take to break those bonds. So that's step number one. And then you figure out all the bonds that are going to form, and you tally up all the energy that you're going to get out when you form those bonds. And then you put those together, you just add them, and voila, you have bond enthalpies. So look at the formula here. This should look very familiar to you. It basically looks like what law? It basically looks like Hess's law, right? So you have the total enthalpy of reaction, you have the sum of all the bond enthalpies for bonds that you're going to break. And then notice you have a subtraction here because the appendix is listed in terms of breaking the bonds. So if you want to talk about forming the bonds, which is the next step, the sum of all the bonds formed, right? You have to flip that sign. So again, you can do that logically, or you can do that just plug and chug into the formula. This formula also, you're going to have to multiply by the number of bonds you break. So if you break like 3 carbon-hydrogen bonds, you're going to take the value for breaking a carbon-hydrogen bond and multiply it by 3. So the N factor in that Hess's law still applies here, right? You still have to multiply for the number of bonds you're going to break. Because if they're listed in kilojoules per mole, you have to multiply by moles to get rid of the moles and come out with an enthalpy of reaction in kilojoules. Okay, so let's look at one of these. All right. We have this reaction. We have methane plus elemental chlorine goes to methyl chloride. or something to that effect, plus hydrochloric acid. So we need to think how many bonds are going to break and how many bonds are going to form. Now you can just bust apart the whole thing and then reform the whole thing. So if we did that, we would have like 4 carbon hydrogen bonds are going to get broken. 1 chlorine bond is going to get broken. Okay, so that is going to be the sum of our bonds broken, and then we're going to form 3 carbon hydrogen bonds plus 1 carbon chlorine bond plus 1 hydrogen chlorine bond. And those are going to be all our bonds formed, which we're going to subtract. Okay, but notice here that you have some repeats. Notice we break 4 carbon hydrogen bonds. You also form 3 carbon hydrogen bonds. So instead of busting apart everything and then reforming everything, what you can do is really evaluate what's going on here and only do the stuff that changes. So carbon, hydrogen, 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 really, and then we have a chlorine, right? So really what's happening here is we're going to take off one of these hydrogens. So we're breaking this bond. We're going to break this bond. And then the chlorine reforms, the chlorine hydrogen reforms. So we can also write this in a more like succinct way where we're going to break a carbon hydrogen and a chlorine, and we're going to form a hydrogen, chlorine, as well as a hydrogen, as well as a carbon, chlorine. Okay, so notice the 2 ways that I've set this up are going to come out exactly the same. And actually, the example here, it gives it to you in the second method because we're chemists and we like to be efficient, also known as lazy, but efficient, right? Okay, so here are values looked up in that appendix in the back of the book. This is the value for breaking a carbon-hydrogen bond. Here's the value for a chlorine-chlorine bond. Here's the value for a carbon-chlorine bond. Here's the value for a hydrogen-chlorine bond. They're all added up. The sign of these are flipped by this subtraction here, and we get an overall enthalpy of the reaction of negative 104 kilojoules. So for this reaction to happen once, we're going to get out 104 kilojoules of energy. Notice it's exothermic. Doesn't always happen. So, but doing this method can tell you if it's going to be exothermic or endothermic. What this means, you should be able to draw this in terms of an energy diagram. So can you take this information and turn it into an energy diagram? That would be a really good thing to pause and find out now if you can do that. I'm going to do it right now too. Okay, so in our energy diagram, because it's exothermic, my reactants are going to be here. My products are going to be here. I'm going to get out negative 104 kilojoules. And there's always this funny line here that goes up and then down. And we're going to talk about that funny line when we get into kinetics. I think so. But you don't have to draw the funny line. If you can draw this as your energy diagram, then you are good to go. You could also get a little more detailed and say, okay, reactants, we have to input this much energy, whatever that is, 650-ish, before we output, I'm going to put that in, 650-ish, before we output this much, which is 750-ish. And that's going to result in our difference of about 100 kilojoules. Yeah, that makes sense. Okay, so could you draw that energy diagram? If not, what pieces were you missing? All right, we're going to do a practice with this together next time, so don't do that yet. And that is our chapter 8. Here's a pretty good summary of what we were just talking about. The number of bonds, bond enthalpy, and bond length are all related. That's chapter 8. We're going to just keep on trucking and go into chapter 9 now. Okay, let me know if you have questions. I will see you in class.